Okay, 8.7, Taylor-Maclaurin series. This is our last week of lecture, right? Okay, so this is fun. The Taylor-Maclaurin series is fun, all right? So we start out with this idea that we have a function. We've defined a function to be this infinite series, right? A power series. And it has some radius of convergence. So let's just say that we have this power series, right? The question becomes, like, I guess, the thing that distinguishes one function from another function, there's only one thing that changes, and that is the c sub n's. Every power series is going to have x minus a to these changing powers. It's really the thing controlling it, or what makes each function unique, is the c sub n, the number in front. All right? So you remember, if I give you a certain type of function, you can convert it to its power series. We did that last week, and what we used was this right here, right? That we know the power series for that. But I was very clear, I hope I was clear, that if I gave you a function and said find its power series, it had to somehow be connected to this, or else we couldn't do it. But I said later on, we'll be able to find the power series for any function. And today is where we start that. And it all is in this section, Taylor-Maclaurin series. So our goal here is to, given this, can we find a formula for c sub n? Okay? Somebody gives us a function. Can we, bless you, can we find some sort of formula for c sub n? So let's write out this power series first. Let's actually write it out. If we start plugging in 0, 1, 2, 3, we'll have c sub 0 plus c1 x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a cubed. I'm going to go out quite a few here. Plus c sub 4 x minus a to the fourth. One more. C sub 5 x minus a to the fifth plus dot, 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 dot. So we have some function. We know it can be rewritten as this power series. We just don't know what these c's are. So is there a way we could somehow generate them, right? So check this out. This is very clever. It's not my idea. That's why it's clever. Okay? What is f of a? What should this function's value be at a? So if I plug a into this function right here, what does it spit out? It spits out c sub 0, doesn't it? Because this goes to 0, 0, 0. If I'm replacing all the x's with a's, everything that has x minus a in parentheses to a power is going to go to 0, right? So c sub 0 is equal to f of a. Right? So don't I know what c sub 0 is? C sub 0 is the function's value at a. That's what it is, right? Okay. Let's see if we can't figure out what c sub 1 is. So how could we figure out c sub 1? Well, again, I'm going to be clever. I'm going to take the derivative of this function first. So take derivative of this function. So what's the derivative of this? 0. Okay, what's the derivative of this term? Just c sub 1, right? Because constant comes for the ride. Derivative of that is 1. So we just get c sub 1. Plus, now, what about the derivative of this piece? So 2 comes out, right? 2 c sub 2 x minus a, right? What about the derivative of this one? 3 comes out, c sub 3 x minus a squared. This one, 4c sub 4 x minus a to the third plus 5c sub 5 x minus a to the fourth plus, and we continue that, right? All right, now why did we do the derivative? Now, I should have started this with do you remember when I was trying to show you the whole idea of that function f of x was cosine x, and we could approximate it? We approximated this function with 1 minus x squared over 2. Remember that? I said the way we did that is we said, look, First, we need these two functions to match at 0. Then their derivatives need to match, and then their second derivatives need to match, right? That's exactly what I'm doing here. I'm saying, look, I want my function this function to match. When I plug in a, I want it to match the function, right? Now I want the derivatives to match. So I take the derivative of the function, and now, being very clever, I'm going to say, what is the derivative's value at a? It's just c sub 1. For the same principle that all those get killed off, right? Okay, so now don't we know what c sub 1 is? So c sub 0 is just the function's value at a. C sub 1 is the function's derivative, the value of the function's derivative at a. So maybe c sub 2 is the second derivative at a. Maybe? It's not that easy. Okay, it's not that clean. Let's just see what happens now. So I'm going to continue. Let's take another derivative. So what would the second derivative of this function be? So take the second derivative. Here's the first derivative, right? Take the second derivative now. So derivative of c sub 1 is 0. Derivative of this one is what? 2c sub 2. Okay, plus, now be careful here, 6, right? Because the 2 is going to come out. Now I'm not going to write it as 6. I'm going to write it as 2 times 3, all right? Because a pattern is going to start to establish. 2 times 3, c sub 3, x minus a to what power? 1. Okay, plus, okay, this one's going to be 4 times 3. I'm going to write it 3 times 4. C sub 4, x minus a to the 2. And then this next one's going to be 4 times 5, c sub 5, x minus a to the 3rd, and so on and so forth, right? So now what I do is I plug in a into the second derivative. What is the derivative, the function's second derivative of the function at a? What is it equal to? 2c sub 2. Okay. Now let's do the third derivative. And I think what I'll do is I'll write these things down over here. We know that c sub 0 was f of a. C sub 1 was the derivative of the function at a. C sub 2 is, well, let's see. Hold on. C sub 2 is what? Because I have to solve for c sub 2. 1/2. I'll do it f double prime of a over 2. Okay? Just solving that for c sub 2. Now let's do our third derivative. Our third derivative, that's gone, right? Okay, this one, 2 times 3 c sub 3. Plus this one, 2 times 3 times 4 c sub 4 x minus a. This one, 3 times 4 times 5 c sub 5 x minus a squared plus dot 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 dot. And now let's plug a in again. So what happens at a? The third derivative at a is what? 2 times 3 c sub 3. So solve this for c sub 3, and we get c sub 3 is the third derivative evaluated at a over 2 times 3. Do y'all see the pattern? Do y'all see it? Do I need to go one more? Yeah, let's go one more. Let's go to the fourth derivative. Okay? Now I'm going to start changing my notation for derivatives. Instead of writing primes, because I'll run out of primes, right? It'll get all. I do fourth derivative, I write f. In parentheses, I put 4. Has to be in parentheses. If you don't put in parentheses, then you're saying raise it to a power of 4. The parentheses means take the derivative. So I want the fourth derivative of the function. So here's our third derivative. So derivative of that is 0. Derivative of this one? 2 times 3 times 4 c sub 4. Plus, this one's now 2 times 3 times 4 times 5 c sub 5 x minus a. And then plus dot dot dot. Let's plug a in again. If you look at the fourth derivative of this function at a, you get 2 times 3 times 4 times c sub 4. And everything else goes to 0 because it has x minus a's in it. So our c sub 4, should be the fourth derivative of the function at a over 2 times 3 times 4. Using this same process over and over, can we come up with a formula for c sub n? We can. What is it? The nth derivative of the function evaluated where? At a, that's important, over n factorial. So do we agree that this one right here, this first one, is the original function, right? When you say the original function, that means you've taken the 0th derivative. So that's the 0th derivative of the function at a over, well, it's got to match the formula, 0 factorial. But what's 0 factorial? 1, okay? And then the next one is the first derivative, right, over 1 factorial. And then the next one is second derivative over 2 factorial, third derivative over 3 factorial, fourth derivative over 4 factorial. Yes? And this is Taylor's formula. This is a formula that allows you to calculate what the constants need to be for every, if someone gives you a function, right? We now have a way of coming up with its power series, so long as we can do this. So this is important though, because you have to understand that we have to know a lot about the function in order to come up with its Taylor series or its power series. We need to know a lot. Don't we need to know the nth derivative of the function? We need to be able to take the derivative over and over and over and over and over, right? And be able to plug in some value into that function. And if we can do that, then n factorial is just n factorial. But this is the part right here that we have to kind of, for each particular function we're handed, we have to figure out what this thing starts to look like, all right? So let's do an example, all right? Make sure there's... Oh, okay, so this is it right here. This is called, let me rewrite it so we have like an official note up here on the board. So given f of x, which equals some, given f of x, sorry, let me say this a different way, where f, I don't think I put it in here, but I should have. No, it's the wording of it. I need to put in here that we need to be able to take the derivative. The nth derivative exists, right? So given a function where f is differentiable, all right? N times. Okay, so we need to be able to take derivative n times. Then f of x can be written as the sum n equals 0 to infinity of f nth derivative at a over n factorial times x minus a to the n. So do you see all I've done is I've replaced c sub n with the formula, right? This is the formula we came up with, right? So all I've done is I've replaced it with this. And this is called the Taylor series about A. It's the Taylor series about A. So someone has to hand us a function. We need to be able to differentiate it n times. If we can do that, then we should be able to write out its Taylor series. Okay? Any questions on that? One more thing on top of this. A Maclaurin series is just a Taylor series about 0. So a Maclaurin series is a very, very specific version of Taylor. It's when A is 0. So what would this formula change to for Maclaurin? It would be sum n equals 0 to infinity. The nth derivative where? At 0. So all you're doing is replacing that with 0, right? Over n factorial. And then this becomes what? Times x to the n. So that's your Maclaurin series. Excuse me. There you go. Yeah? I'm not sick, but just to be safe.
I think we're all a little bit.
Yeah, my neighbor mowed the grass yesterday while I was outside putting up Christmas lights, and I mean, there was like a layer of dust and debris on my car, so I'm sure I ingested a lot of that. Okay, so a Taylor series, the one way you can think about this is like Taylor series is like a rectangle, and Maclaurin series is a square. It's like a specific kind of rectangle, right? All right, so you ready to do an example? All right, here we go. Find the Maclaurin series for f of x equals cosine x and its radius of convergence. Notice I did not ask for the interval of convergence. Right? Okay, interval of convergence would be a harder question. Okay, find the Maclaurin series. All right, so they've given us a function, right? Are we going to be able to take the derivative of that function over and over and over? Yes? We should be able to. So the way I like to start these problems out is I like to start to make a table. All right, so what I'm going to have over here is I'm going to have my function, its derivative, its second derivative, its third derivative, its fourth derivative, its fifth derivative, and then maybe, if I'm lucky, I might be able to come up with a formula for the nth derivative. I don't know yet, okay? So I'm going to have that, right? These are just going to be all my derivatives. Then, separate from that, I'm going to look at that evaluated at A. And if it's a Maclaurin series, what's A? 0. So I'm going to try the function's value at 0, then the first derivative at 0, then the second derivative at 0, and then the third derivative at 0, then the fourth derivative at 0, and then the fifth derivative at 0. And then maybe, if I'm lucky, I can come up with a formula for the nth derivative at 0. So there's a difference between this and this, right? This is just the derivative of the function. Then here's me plugging in the value of A into each one of them. So let's go with this. F of x is cosine x, right? Derivative of that? Minus sine x. Derivative of that? Negative cosine x. Derivative of that? Sine x. Derivative of that? Cosine x. I'm back to cosine, right? Now everything's going to repeat. Negative sine. And well, let's leave the nth for now, okay? Dot, dot, dot. You get the idea? Okay, so now let's plug in 0. So what's cosine of 0? 1. Okay, plug in 0 into this. 0. Okay, here. Negative 1 here. 0, then 1. And then what's it going to keep doing? repeat. It's going to go 1, 0, negative 1, 0, 1, right? It's going to keep on repeating itself. And that's because the cosine function, when you take its derivative, is what we call cyclic, cyclic. So it's a cyclic derivative. Okay. Now, we want to try and come up with the Maclaurin series. So we want to try and rewrite this like this. Right? That's what we want to do. But in order for us to do this, we need to have a general formula which would be this. Do y'all see that? We need a general formula for the nth derivative at 0. Now we know it's either going to be 1, 0, negative 1, right? It's going to be one of those things. It's either a 1 or 0 or a negative 1. That's what it is. So we could come up with a formula, but it's actually kind of complicated in this example to come up with the formula. I mean, we could do it, but there's another way to approach this, which I think is easier for this problem. So watch. I'm just going to rewrite this, okay? This is equal to, let's just plug in n equals 0. So we plug in 0, we get the 0th derivative at 0 over 0 factorial x to the 0. Do y'all agree that's me replacing all my n's with zeros? Okay, plus now it's the first derivative at 0 over 1 factorial x to the first power, plus the second derivative at 0 over 2 factorial x squared. With me? Plus third derivative at 0 over 3 factorial x cubed. I'm going to be off camera here, I think. Can I just continue below this? Yeah? Okay, so plus, what do we got? Fourth derivative at 0 over 4 factorial x to the 4th, plus fifth derivative at 0 over 5 factorial x to the 5th. I'll go one more. Sixth derivative at 0 over 6 factorial x to the 6th plus dot, dot, dot. Do y'all agree that's just it written out? So keep in mind, I'm doing this because I don't have a nice, clean way of coming up with a formula for that, right? So I've decided to write it all out. Now let's start plugging things in. Okay, equals. All right, do we know the 0th derivative of the function at 0? That's the 0th derivative, right? That's the 0th derivative of the function at 0. What is it? 1. So this right here is 1 over 0 factorial. Agreed? So that's just 1. X to the 0, which is 1. So the first thing is 1. Okay, now we move on. Plus, what is the first derivative of the function at 0? 0, right? That's right here. 0 over 1 factorial times x to the first power. 0. Okay, plus this one. What's the second derivative of the function at 0? Negative 1 over 2 factorial, which is just 2, right? I'm going to write it as 2 factorial, though. So negative 1 over 2 factorial x squared, right? With me? Okay, what about this one? Third derivative at 0. 0, right? It's gone. So plus 0. Plus, okay, what about the fourth derivative at 0? We're back to 1, aren't we? The fourth derivative at 0 is back to 1. So we're going to have 1 over 4 factorial x to the 4th. Are you all good up to that point? What can you tell me about the 5th derivative at 0, the 7th derivative at 0, all of the odds? They're all zeros, right? Like first derivative, third derivative, then we're going to start repeating. So my next term, and I am going to run out of room here, but my next term is going to be 0 again, right? That's the one from the 5th power. Now what about the 6th power? So where are we on the 6th? So this was, so we got to repeat this. We got to repeat this pattern. It was 1, 0, 1, 0, and then what? Negative? So we should have a negative 1. So I'll do it right here. Plus negative 1 over what? 6 factorial x to the 6th. Plus, we're now at an odd, right? Odd is 0. Plus, now we're on the 8th one. So we've gone from negative 1 here to 0. Now we're back to 1. So positive 1 over 8 factorial x to the 8th. Let's just go a couple more. Plus, what? 0 plus, now we're at negative 1. Negative 1 over 10 factorial x to the 10th plus dot, dot, dot. Do y'all follow that? Okay. We're getting there. We're getting there. Hold on. Let's get rid of all those zeros. 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th minus 1 over 10 factorial x to the 10th plus dot, dot, dot. Yes? Back to a series now, summation. Okay? Sum n equals 0 to infinity. All right, so now just want you to kind of clear your minds. And if you were asked to take that and rewrite it in sigma notation, let's see what we've got going on. It's alternating, positive, negative, positive, negative. How do we make things alternate? Negative 1, in this case, to the n. Be careful because we're going to start at 0. Okay? Be careful, we're starting at 0. So you want just n. Just n. Because we're starting at 0, right? So negative 1 to the 0 would be 1. Okay, so I want it to start out at positive. So that should take care of my alternating, right? Okay, let's see what we've got next. All of these numerators are 1, 1, 1, 1, 1. Over, what factorial are these? These are all even numbers, right? Even numbers. 2, 4, 6, 8, 10. Those are all evens. But starting at this one right here, what's under here? It's really like a 0 factorial on the bottom, isn't it? And n is starting at 0. So 2n in parentheses factorial. So if n is 0, what do we have? 1, right? If n is 2, if n is 1, we have 2 factorial. If n is 2, we have 4 factorial. If n is 3, we have 6 factorial. See that? Okay. What are we missing? The x's, right? So, but all those are even powers again. 2, 4, 6, 8. So x to the 2n, we want to start here at this first one. What's the x power here? X to the 0, right? So just 2n should work because we're starting at 0, right? Do y'all agree with that? There it is. That's your Maclaurin series for cosine.
So that was fun.
The whole day is going to be fun.
I mean, I had fun.
Where did my drink go? Oh, there it is. Thank you.
No.
We're not done. We're not done. Radius of convergence. So, do y'all remember when I first introduced this whole idea, I did the graph of cosine. I said, what would be a good approximation of cosine? And we had said 1 minus this, right? Remember that? And I stopped there. I didn't do all that. But I said later on we'll see that we could do more terms and you would get a better approximation. This question of radius of convergence is asking how far away can we go from 0? Because remember, this is the Maclaurin series about 0. How far can we go away from 0 and still trust that this series is accurate? How far are we allowed to go? And that's what the radius of convergence will tell us, right? So let's see. Let's see if we can find the radius of convergence. How are we going to find the radius of convergence? Well, this is our power series, right? I'm asking for the radius of convergence of this power series. So ratio test. Just run a ratio test on it. So if I do a ratio test on that series, I'm going to take the limit as n goes to infinity of, now remember how to do this? Well, you better, because in a week you need to know. By the way, we should talk about the final when it is. It's on Monday. Your final's on Monday.
What time?
11 o'clock. Next Monday.
So the 9th?
What's wrong? Okay, Monday at 11 till 2. 11 till 1:45. 11 to 1:45. We'll talk more about that later. All right, so ratio test. So what we do is we take this, right? We plug in n plus 1, and then we divide that by this just with n in it. So if you've been doing your homework, you've done this a lot. Negative 1 to the n plus 1, x to the 2 times n plus 1 over 2 times n plus 1, that whole thing factorial. Okay, so what I did is I put this and the x and the negative 1, I put those together on top. And I put this 2n factorial on the bottom. But notice, I mean, all the n plus 1s are being replaced, or all the n's are being replaced with n plus 1s, right? And then I divide by this, which is the same as multiplication of the reciprocal. So I put 2n factorial here. And on the bottom, negative 1 to the n and x to the 2n. Okay, so what I need to know is when is that limit less than 1, right? That's what the ratio test is asking. When is that less than 1? Okay, I can ignore what? What can I ignore here completely? These negative 1 to the n's are gone. This right here can be rewritten how? X to the 2n times x squared, right? This can be rewritten as 2n plus 2 factorial, right? And what do I need that to be so it can cancel out with the other thing? 2n. I need this to be, I need a 2n factorial out of this one. So I start peeling off things, right? So I would subtract 1 each time. So 2n plus 2 peels off, 2n plus 1 peels off, and then I'll have 2n factorial. So that becomes this. Right? And now we start to get a lot of really nice cancellation here. The x to the 2n cancels with the x to the 2n. The 2n factorial cancels with that 2n factorial. And I think I have everything I need to continue. Are there any questions while I'm erasing this? So this becomes the limit as n goes to infinity. And this is where I said separate your x stuff from your stuff that's not x's. So the only thing that has x in it still is x squared, right? So I'm going to put that over here, x squared. All right, and then what else is left in terms of n's? Just that stuff down there, right? So 1 over 2n plus 2 times 2n plus 1, right? And if you let n go to infinity, that goes to 0 and x is basically eliminated, right? So the question is, when is that less than 1? For what values of x is this going to be less than 1? All values of x. So what's your radius of convergence? Everything. R is infinity. Which means that that power series, that Maclaurin series, is valid for any value of cosine. So if you want to know what cosine of 5 was, you could just take that power series and replace all your x's with 5. And it would give you an accurate answer. As long as you go out forever, okay? You have to take the power series out forever. But it's not going to fall apart. It's not like the power series all of a sudden has this really bad issue. We saw that with power series that have a radius of convergence on an interval or something. We have issues. Once you go outside that interval, the power series is no longer valid. But with this cosine function, the Maclaurin series for cosine is valid always. Okay? Questions?
Yes, so it's supposed to be less than 1 for it to be convergent, right?
If it's less than 1, anytime the ratio test gives you the limit, right? That thing is less than 1, you have a convergent series.
Right.
But we're saying for what values of x will this be convergent? And because that goes to 0, x doesn't matter. X can be anything you want it to be. So as long as you fix a value of x, like give me a number, boom, it doesn't matter. That's going to 0. It's going to kill it off. And remember, you cannot plug infinity in. Okay? You can't, because you're looking at x is the input into a function. And that can only be a real number. And infinity is not a real number. You could give me a billion, gajillion, gazillions, but even if you give me a billion, gajillion, gazillions, if I let n go to infinity, it's eventually going to become, this is going to go to 0 and it's going to overwhelm that. Okay. What do you think the next natural progression of things we should look at the Maclaurin series for should be? Maybe sine? Let's go with sine. I don't think it's going to be too different, right? I mean, there's a lot of similarities with sine and cosine. Okay, you ready to do the Maclaurin series for sine? Wonderful, let's do it. Sine x. All right, now I won't do its radius of convergence. It turns out that it's the same, okay? I'm not going to go through the exercise, but let's just find the Maclaurin series. So we start out. I'm going to start writing this way. The 0th derivative at x, the first derivative at x, the second derivative at x, the third derivative at x, the fourth derivative at x, fifth, okay? So let's go ahead and take these derivatives. So sine x, that's no derivative. Cosine x, negative sine x, negative cosine x. Then sine x, cosine x, and it's going to start repeating itself, isn't it? Sine, cosine, negative cosine, sine, cosine, negative sine, negative cosine. So those are just my derivatives. Now what I need are the derivatives at what value? At 0. Why 0? For Maclaurin at 0. Okay? Okay. We're going to get a repetition here, aren't we? We're going to get repetition? Okay, here we go. What do we got? 0, 1, 0, negative 1, 1, and then it's going to be repeating. 0, 1, negative 1, sorry, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, right? Over and over and over. All right, so now we go and we try and come up with, for sine of x, its Maclaurin series is the nth derivative at 0 over n factorial x to the n, right? That's the general Maclaurin series formula. It would be really nice if I had a formula for this, right? I don't have a formula because of the way it's cyclic, it's hard to generate this formula. There's going to be an example I do after this where we can actually come up with the formula right here, and we never have to write it all out. But let me show you this example. Okay, so what should I do next? What did I do last time at this point? Just start plugging in n equals 0, 1, 2, 3, and just, okay, so we're going to have the 0th derivative at 0 over 0 factorial x to the 0 plus the first derivative at 0 over 1 factorial x plus the second derivative at 0 over 2 factorial x squared plus the third derivative at 0 over 3 factorial x to the third. Am I going too fast? I feel like I am, yes. Yeah. Maybe one more. Fifth derivative at 0 over 5 factorial x to the fifth plus dot, dot, dot. First term. What's the 0th derivative of this function at 0? 0. Okay, so the first term's gone. All right, plus. All right, now the first derivative at 0, first derivative at 0 is 1 over 1 factorial. So it's just going to be x. I'll write it out, 1 factorial x. In fact, this 0, 1, I'm going to write it down. 0 over 0 factorial x to the 0, just so we can see what it was. All right. And then this one is that. And then this next one, second derivative at 0, 0. So 0 over 2 factorial x squared. That's all going to go away. This one, third derivative at 0. Negative 1 over 3 factorial x cubed. Next one. 0 over 4 factorial x to the 4th. Next one. We're at the 5th. 1 over 5 factorial x to the 5th plus dot, dot, dot. All of the even powers of x are gone, right? The only thing left are the odds. Sine is an odd function, right? That's why. Cosine is an even function. That's why. So I mentioned this a while back, yes? Like back in college algebra when you're learning about even and odd functions, they tell you what they are like algebraically. To be even meant that f of x was equal to f of negative x. Remember that? That's what it meant to be even. And to be odd, it meant that f of negative x equals negative f of x. Back in college algebra, that was the definition of even and odd. Now in calculus, your definition of even and odd is what is its power series. If its power series is just even powers of x, it's an even function. If its power series is just odd powers of x, then it's an odd function. If it has a mixture of even and odd, then it's neither even nor odd, right? There's only three possibilities. Your function's either even or odd or neither. Okay, are we ready to try and come up with this now? Write this out. Let's see, all these are gone, right? So maybe we can write the summation formula out now. Are y'all ready for the sum? Okay, so this should be equal to sum n equals 0 to infinity. It's alternating. Starting with positive, then negative, then positive. So we know how to do that. It's negative 1 to the n because we're starting at 0. That should start out positive. Okay, let's look at the numerators. 1, we already took care of the negative. All the numerators are 1s, right? 1 over. Okay, what about the denominators? 1 factorial, 3 factorial, 5 factorial. Odd numbers. 2n. Careful, we start at 0, close. 2n plus 1. Factorial. Everyone agree? If n is 0, you get 1, right? If n is 1, you get 3. So this starting at 0 is kind of tweaking a little bit of what we've done. When we first started talking about sequences, we always started at 1, right? But now that we're here, we're starting at 0, and we're just making a slight adjustment in this. Yes?
Question. So how would you get it to be 0 factorial if you have 2n plus 1?
I don't. I'm ignoring this. This is no longer here, right?
Okay.
Right? I'm saying forget this. I just need to make, I need to just make that happen. If I can make that happen, right? I don't need to make the zeros happen. So I'm just focusing on what I have there. Alternating starting with positive, 1s in all the numerators, odds in all the denominators starting at 1, and then what about the powers on x? 2n plus 1 again. X to the 2n plus 1. That should get us, x to the 1st, 3rd, 5th, 7th, so on and so forth. That is your Maclaurin series for sine. Its radius of convergence is infinity. Yes? It's fun. I told you fun. I'm delivering fun.
Merry Christmas.
Merry Christmas. Yes. Okay, let's go e to the x. E to the x. Yeah. Yeah.
The derivatives are
Yeah, this is going to be so clean and easy because the derivatives are all the same. So wait a minute, hold on. Do I really even need a table?
No.
What is the nth derivative of this function? Okay, e to the x. I don't even have to think about that, do I? Now, what is the nth derivative of this function at 0 because I want the Maclaurin series? 1, right? Just plug 0 into that and you get 1. So it's 1 all the time, isn't it? So if I look at e to the x as its Maclaurin series, I needed this, right? And we've had to actually write this thing out in the past because we didn't have a clean formula for this, did we? We didn't. But here, because the cleanness of e to the x, this top part right here is, what's the nth derivative at 0? It's 1 all the time, so that's 1 over, what, n factorial? X to the n. Done. That's it. That's your power series, or that's your Maclaurin series. Now let's write it out. Let's just see what it looks like. If we let n be 0, what do we get? 1. Does it alternate? I don't see any alternating parts in here, do you? Okay, 1 over, now we're plugging in what? 1, so 1 over 1, x to the 1, plus 1 over, well, I should say 1 factorial, it doesn't matter. 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on, right? And I've shown you this already, that if you take the derivative of this, you get itself, right? Like if you take this derivative 1 is 0, derivative of this is x. Derivative of x is 1, so you get that, and derivative of this one would be that one, and derivative of this one would be the one in front of it, and you basically get the same thing. Really awesome series. Okay, good?
Everybody groaned on that.
Yeah, and everyone was so upset. All right.
I groaned to be dramatic.
All right, so now I get to show you the cool thing.
Insert groan here.
We're going to do more of these, but this is a great opportunity for me to do the following. Okay, so I've shown you this. Okay, I've shown you this. This is arguably the most beautiful equation in math, okay? And have I mentioned why? Do we need to go through why we call this? Has all the most important numbers that we use in math. Like, they're all there. Like, you know, we all know pi is important, right? We all know e is important. I gets a bad rap because most people think imaginary number is imaginary. But it's not. It's not. I mean, that's all I'm going to say because I could just go off on a tangent on that one. Then, of course, 1 is important. That's our multiplicative identity. Okay, that's part of what makes our number system a field, is the fact that we have a multiplicative identity. And 0 is our additive identity. And all fields have to have both a multiplicative and additive identity in order to be considered a field, along with 12 conditions to be a field, all right? So this like all the good stuff's right there, right? So I'm going to try and prove this is true, okay? Try and prove this is true. You ready? So would you all agree with this? If I can prove this is true, you'd be satisfied? I'm trying to show you that e to the I pi is going to be equal to -1. Yes? All right, so wait a minute. Hold on a second. What is e to the x? 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 6th plus, I'll do one more, 1 over 7 factorial x to the 7th. Do you all agree with that? Didn't we just prove that a second ago? Okay, well, let's replace x with I times pi. All right, but let's keep something in mind. Let's just keep something in mind. I is I, right? What's I squared? What's the definition of? I squared is negative 1. Heidi, what's going on? Did I mess something?
5 factorial x.
Oh, yeah, I'm sorry, I messed this up. 5 factorial 5, sorry. I'm missing one here. 6. Thank you, Heidi. You don't have to take the final. Good job. No, I'm just kidding. I'm kidding. I'm kidding. Okay, so I squared is negative 1, right? Just out of curiosity, what would I cubed be? Well, wouldn't it be just that times I? So negative I? Agreed? And then what would I to the 4th be? Well, that would be I squared times I squared, right? So that would be this times itself, which would be 1. And then what would I to the 5th be? It would just be I again. So what I'm doing is I'm starting out with the fact that I to the first power is I squared is negative 1 by definition. That's what I is. I squared is negative 1. I cubed would just be negative I. It's this times I. Then if I hit that with another I, it's I to the 4th, which is basically squaring that one. Now I'm back to 1. If I multiply that times I again, I get I, and then it's just going to keep being cyclical after that point. Agreed?
I'm sorry, I'm not following how I squared is somehow negative 1.
That's the definition of I.
Oh.
I, by definition, is what you get when you take the square root of negative 1. So I is the only number, it's a complex number, that when you square it, you get a negative result. All right, you ready? So check it out. We're going to go in here and we're going to replace x with I times pi. Okay? I times pi. So 1 plus x, which is I times pi, plus 1 over 2 factorial, what, I pi, but then squared, plus 1 over 3 factorial I times pi cubed, plus 1 over 4 factorial I times pi to the 4th, plus 1 over 5 factorial times I pi to the 5th, plus 1 over 6 factorial I pi to the 6th, plus dot, 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 right? All right, let me keep going here. This is 1 plus I pi, because it's just I times pi. Okay, now over here, when I square I, what do I get? Negative 1, right? So really this I is gone, but it changes this to a minus, right? So I'm going to go minus 1 over 2 pi. The I is gone, but I still have what? Pi squared. Okay? Okay, this one. What is this going to be? I have I cubed. What's I cubed? Negative I. Do you all agree with that? So I have negative 1 over 3 factorial. I still have an I here, don't I? So I'm going to go I, but I have pi to what power? Cubed. Does everyone see how the I cubed turned into a negative I? Next one. Plus 1 over 4 factorial. I to the 4th. 1, so it's not there. Pi to the 4th. Plus, okay, what about I to the 5th? We're back to I, aren't we? We're back to I. So 1 over 5 factorial I pi to the 5th. So I did the 5th power on the I and got just I, and then I did the 5th power on pi, right? Okay, let's do maybe one more. What's this one going to be? What's I to the 6th?
Negative 1.
So where are we? We were at I, right? So coming back cyclic, we should be here, right? Negative 1 should be our next one. So negative 1 over 6 factorial, right? And just pi to the 6th. Okay? Let's see that? Do I need to go any more? Sure? Let me go one more, sorry. I'm going to go one more, because the next one is I to the 7th. Where are we going to be at I to the 7th? We're going to be at negative I, right? Okay, so we're going to have minus 1 over 7 factorial I, and then pi to the 7th, plus. All All right. You ready for the coolness? I mean, it's already cool, but you ready for the super coolness? Okay. See those? Those all have I in them, don't they? The others do not have I in them. So I'm going to change this. I'm going to write this as 1 minus 1 over 2 factorial pi squared plus 1 over 4 factorial pi to the 4th minus 1 over 6 factorial pi to the 6th plus dot, 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 dot. That takes care of everything that doesn't have i's in it, right? Then I'm going to say plus now the stuff that does have i's in it. Now, everything that has an I in it, that has an I, they all have one I, right? I'm going to factor the I out. The I's coming out, and then what's left? If I take I out of this, what am I left with? Pi, right? And then what? This one right here, I took the I out, so minus 1 over 3 factorial pi cubed, plus this one, 1 over 5 factorial pi to the 5th, yes? Minus 1 over 7 factorial pi to the 7th, plus dot, dot, dot. Okay? Do y'all see it? Does this look familiar to you? What is that? That's cosine of what, though? That's cosine of pi. Remember, cosine of x is 1 minus 1 over 2 factorial x squared plus 1 over 4 times 1 over 4 factorial x to the 4th, right? Minus 1 over 6 factorial x to the 6th. So isn't this just cosine of pi? Yes? Okay, plus I times, do you recognize this? That is just sine of pi. And what is sine of pi? Sine of pi is 0. What is cosine of pi? Negative 1. There it is. E to the I pi is negative 1.
You already know, man.
Right? E to the I pi is negative 1.
Some witchcraft for that.
It's cool stuff, right? So this is actually really even more profound, I guess, is what if I would have just left this, and instead of pi's here, I just would have left it as a variable like x, like e to the ix. Then everywhere I see pi's would be x's, right? So x is here, x here, x here, you know, x, x, x. And then now what we would get instead of this, right, what would we get? Cosine of x plus I times sine x. And that you may recognize as being called Euler's formula. This is something you may have covered in pre-cal. Maybe, maybe not. But e to the ix is equal to cosine x plus I sine x. That's an important formula. It comes up quite a bit later. Let me see if I can't make that make a little more sense to you. Watch this. See if I can kind of blow your mind a little bit. Okay. So let's say, I don't know how much of this you're going to remember, how much you've even how many of you in college algebra talked about complex numbers at all? Like with the I in there? A little bit? Okay, so let me just show you something. Okay. Let's say that we have the unit circle. Okay, 1. And I take this point right here, which we know is root 2 over 2, root 2 over 2. Let's look at this number, root 2 over 2 plus root 2 over 2i. This is a complex number. This is what we call the real part, and this is the imaginary part. So to get to this number, you go out root 2 over 2, up root 2 over 2. And this right here, this y-axis is actually called our imaginary axis. Again, this is going back to a long time ago, all right? But I want you to see something here. According to, I guess the relationship between this point and this is that if you look at the angle, what is the angle right here? What's that angle? 45, pi over 4, right? Look at this formula. What's cosine of pi over 4?